workshop. The speaker with us is Professor Sushmita from ISI Kolkata again. She received her PhD degree in computer science from Indian Statistical Institute, ISI Kolkata, in 1995. She's had so many awards, and the list is quite big, so I don't know how many to think about. But let's say she was a fellow of IEEE in 2012. She received SINPA India UNESCO Fellowship from International Center of Pure and Applied Mathematics France in 96. I'm just reading quite a few. She's a vice chair of IEEE Women in Computation Intelligence from 2010. She's a member of IEEE System Course from 2012. She is an editor of many journals. Even if I start listing them, we will end up this session. So let's forget that. She is a funding associate editor of Wiley Data Mining and Knowledge Discovery. She is an associate editor of Information Sciences and many more. She has already published 66 journal papers in international reviewed journals and co-authored 3 books, edited 11 volumes in the span area of patent recognition, drug science, etc. She has 2 patents. And with this introduction, I would like to ask her to please come on the dais and start the presentation.
This is the last session, as Dr. Kincher said just now. So this is, you have already been introduced to the different techniques and tools of software. So I will be dealing with the hybridization or the integration involving a few of these. Of these, Neuro-fuzzy is a very common and well-known integration. It is one of the oldest integrations because fuzzy sets came first and then neural networks. Of course, they are older in age than the other components. So in Neuro-fuzzy hybridization, we try to take the advantages of both the neural networks and the fuzzy sets in the broader framework. Now it is often found to be more effective, but again, when in easy problem solving where you can do it with simple tools, one should not go for such complicated things, but only in real life situations where there is a lot of ambiguity, you need a lot of learning. In such situations, we need this sort of techniques. Now in Neuro-fuzzy hybridization, as it is written there, the artificial neural network component emulates the architecture and information representation capability of the architecture of the human brain, while the human reasoning and the uncertainty handling of the is mimicked by the fuzzy sets. So now we can have 2 ways of hybridization. One you call the fuzzy neural network, the other you call the neuro-fuzzy system. The neuro-fuzzy system is more used in control strategies, like you may have heard about the neuro-fuzzy washing machine and things like that. So there what happens is there are a set of rules which are control rules required to control the process, and the fuzzy system provides the rules which are augmented by the neural network. So the rules are built on the neural network architecture. The architecture models the rules itself and they are learned in the environment to provide the neuro-fuzzy computing. In fuzzy neural network, on the other hand, we have the neural network at the base, and we introduce the fuzzy set components at the input or the output or at the neuronal level. The input, instead of 0, 1, you could be providing linguistic inputs. At the output, instead of 0, 1, you could be providing, well, we already have continuous values, but if they have membership concept related with them, some class membership, they could be linguistic also. So then at the output you are implementing the fuzzy concept. And at the neuronal level, so at neuronal level what happens is basically we compute sum and product of the input neurons and the connection weights. Product of that, and then you sum over all the inputs. So instead of that, you could be using some aggregation operator like AND or many other fuzzy aggregation operators. So these are the 3 ways in which you can incorporate fuzzy concepts into the neural network framework, and that is the fuzzy neural network. There can be another way of integration also, that is in normal backpropagation multi-layer perceptron. What we do is we minimize the error at the output layer. Instead of the error as the objective function, you could be using some fuzzy measure which is optimized. Let us say entropy, fuzzy entropy, or index of fuzziness. There are some such measures. So instead of optimizing the error, the plane error, we could be using some fuzzy measure to be optimized. So these are the 4 ways in which you can get fuzzy neural network. So one way is input, you make it fuzzy, another way is output, you make it fuzzy, another way is the operation, you make fuzzy, and the 4th way is the optimization function, that is made fuzzy. Whereas in neuro-fuzzy system, it is mostly used in control. So what we get is, we get the generic and application specific merits of both into this hybridization. So the neural network provides the massive parallelism, the robustness, the learning capability at the generic level, while fuzzy logic provides the ability to model imprecise and qualitative knowledge and handle the transmission of uncertainty. And application specific merits, like in classification, for example, ANN is able to generate highly nonlinear decision regions, and fuzzy logic is able to handle uncertainty in the input description and output decision. So in neuro-fuzzy hybridization, you are incorporating all these merits together. So this is a graphical presentation of the thing. So you've got the neural network into the fuzzy membership concept. This is what I have already explained. The fuzziness could be an input or output. This is the neuro-fuzzy computing. The fuzzy decision system or control system is implemented. Then fuzziness could be at the neuronal level, and the measure of fuzziness could be used as the error or the energy function. It has been established that the fuzzy rule-based systems and neural networks are equivalent. And neural network and fuzzy, there are mathematically established papers on this, not very recent also, quite old. So these two systems are equivalent. Then neural networks and fuzzy sets estimate input-output functions without mathematical model and can learn from data. So both are capable of that. Now, fuzzy sets are advantageous in the logical field. They provide a powerful framework for expert knowledge representation because the fuzzy rules are more human understandable, and instead of numerous numerical rules, you can replace them by a set of finite set of fuzzy rules to efficiently represent expert knowledge, which is more understandable to the human end user. Whereas neural networks provide the flexibility produced by learning, and they are suitable in data-driven processing situations where you have a large amount of data. Linguistic rules. Linguistic rules represent rules in their natural form. That means they should, natural form means like we don't say that the temperature, the fever, in case of the temperature of the weather, let's say. Instead of measuring accurately in degrees centigrade or Fahrenheit, we could use the term hot or humid or warm or cool. These are more understandable to human users. So this is what is called natural forms. So in natural form, when we represent the rules, it enhances their comprehensibility for humans, and for that we need the fuzzy set theoretic concepts. Similarly, neural networks can be trained by numerical data and linguistic knowledge, and fuzzy sets can be designed by linguistic knowledge and fuzzy rules extracted from neural networks. So these are bidirectional relationships between the both of them. Now, in fuzzy systems, there can be two types of rules. One is the Mamdani type of rules, which is of this form, where the antecedents and the consequent, that is the AIs and the Bs, are all linguistic terms. So if x1 is low and x2 is high and so on, then y is warm or something like that. So A and B are all linguistic terms. This is the Mamdani type of rule. Mamdani was an Indian origin scientist settled in United Kingdom. So there. So now we have to have fuzzy membership functions associated with the linguistic terms. Another type is the Sugeno-type rules, where the input has linguistic terms, but the output is numerical. So A0 plus A1x1 plus ANXN. So it provides a functional consequent which provides higher precision. But here the understandability is better to the human brain. Now, but powerful learning techniques which involve a lot of mathematics can be better represented in this framework because you have higher precision. But here you have higher understandability, better understandability. So these are the two major types of fuzzy systems which employ the control rules, and they can be of these types. With this, we go to rule generation. This is one of the work that we pursued. That was during my doctoral work. Actually, it was in 1995, published in 1995 in ITP, Transactions of Neural Networks. My thesis was on neuro-fuzzy computing, pattern recognition. So that was this work was on rule generation in the medical domain. So what we did was some data may be missing. For example, if you go to a doctor with a certain disease condition, the doctor will first of all not send you for MRI tests, which is expensive and not available everywhere. Maybe first the doctor may measure your temperature and other physical, clinical parameters. Maybe go for simple X-ray, and if there is inconclusive evidence, then what a good doctor would do, or a reasonable doctor. Of course, there are business people who will go first for MRI, but the standard practice, I believe, suppose is going from the lowest level. And then, depending on the requirement of information, you go to the more and more complicated and more expensive tests until you are able to arrive at a decision. So this sort of thing was implemented in the sense that some examinations may be risky for the patient, an urgent diagnostic decision is required, and some prolonged test results are excluded, or maybe appropriate technical equipment are not available. So some of the input may be missing. All the input that is required at the end of the day may be missing. May not be required also in some cases. Now the network was provided as input those information, and it may be able to arrive at a decision with that small amount of information depending on the situation. But if it is unable to arrive at a decision, then the network queries for more information, and as it becomes necessary to infer a decision, and then as more and more input is queried from, then it may arrive at a decision at some point of time. And even if the system arrives at a decision, the ultimate diagnostic decision rests with the physician, because any patient would be nervous to just depend on a machine providing the diagnosis. So medical expert systems are supposed to help the physician in arriving at a diagnosis. And so in this system, what we did was the final responsibility of the decision remained with the physician, who verified the justification behind the decision reached, because the neural network was trained. So the rules were extracted from the connection weights, trained connection weights. The system was able to explain its reasoning for an inferred decision in rule form and to convince the user of its correctness. So this was the block diagram, the input pattern components. Some were known and some were unknown. This was the trained neural network based on this data. And then depending on the weight values, the if part was extracted and the output decision with a certainty measure was provided. If the certainty measure was below a certain value, then the output neurons are said to be unknown. You don't get the then part, you go back to the query situation, you query for more information, and it may be available or not available. If it is available, it is provided. Again, this process is repeated. Again, you go there, and if you can arrive at a decision with a certain amount of certainty, then the then part of the rule was generated. So here, from the connection weights, we could get the if part, and here from the certainty measure and the output decision, we could get the then part of the rule. And sometimes it so happened that some input is not available. Then that input is marked marked as unobtainable, and when it is marked as unobtainable, we provided the input as a value 0.5 because 0.5 is the most ambiguous point between 0 and 1. So this was the model. It was of 1995. So the characteristics were that the input was in numeric, linguistic and set theoretic forms. So numeric, you know, linguistic means it could be low, medium, high. Set forms means we were using some descriptive phrases like more or less, very, things like that. So about 90, more or less low, very high, terms like that. These were also possible at the input. And the output was a soft decision provided as unconstrained membership value. The inferencing was based on partial or complete information because when some input was unobtainable, then it was said to be partial, and if it was available ultimately, it was complete. And the querying was provided in case of incomplete input. Rule generation was done to justify a decision.
Set forms are can be replicated with linguistic code.
No. In this case, in this paper, what we did was if it was already low, then the further definition, very low or more or less low.
That is connected to linguistic.
Yeah, connected to linguistic form. Hedges, right, hedges. Also, we have numeric in the sense about 700, less than 800, these values. So these we used to modify. Actually, what we did was, okay, I think I have. So what we did was, each input was actually split into three terms. Like, let's say you had between, let's say the input value was lying between 500 and 1000. So we normalized it to 0 and 1. Now there, we divided that space into three linguistic terms and then mapped it to some membership value in these three linguistic sets. And then we tried to see who was nearest from it, whether low or very low, or very low would give a sharpening of the, it was narrowing the set, and more or less low would broaden the set. Like this. So if low was so by that we saw which one was fitting most closely to the input pattern, and that was extracted. Now this is about the output. So this was how the confidence was defined at each node in layer H plus 1, node J, and the sum of weighted information unknown from the preceding layer, unknown neurons, and sum of weighted information for the known component from the non-ambiguous preceding neuron. So if at the input something is unknown, that is percolating up to the output layer. So that is influencing how much component is unknown, how much component is known at each neuron. So if at any neuron the known component is less than the unknown component, then this parameter was set at 1, that means this would be unknown again. And otherwise it was set at 0, so this would contribute to the known component of the following one. And the certainty measure was computed as this belief function. And then once that was done, let's say this was the trained network, these were the connection weight values, then the paths extracted, let's say the selected paths were the bold ones, and the selected, these are the selected neurons and these are the non-selected neurons, and, which are not matching with the input, and these are the paths which are not selected. So depending on that, the path weights were computed. So let's say this is the feature value of the test pattern, this is the feature value of the second feature value of the test pattern, and it was found to be closest to very medium, and this was found to be closest to high. So the rule was F1 is very medium and F2 is high. Then likely class 1, because again the certainty factor was near likely. We had very likely, more or less likely, things like that. The other details are given in the paper. I am just giving an overview. Now if at any point one feature is unknown, we put this sort of value, and then we computed the known component and unknown component, and in this case both the hidden units are having known component less than unknown component, so the output is unknown, and so you have to query for this F1. Without F1 you cannot arrive at a decision. Now it could have happened that the known component is greater, then you don't need feature F1 to arrive at your decision. This was the logic. And these path values you see for M1 it is 1.6, I'll show you. M1 is this one, so 0.9 and 0.7. The path value is 1.6. For H2 it is 0.7 and 0.4. That is 1.1. Like this we computed the path. No, this was a plain neuro-fuzzy model. With the input was linguistic, output was membership, and that's all. So we did the training. After the training, these were the weight values extracted.
Very high and high.
Yeah, very high or high, they will have some value in these three components.
How can we take the weighted sum of the linguistic variables using some aggregation of?
So, see, a particular value F1. This was the value F1, 0.49. Suppose some value X was there, which was mapped to the three components.
Already defined. Like very medium, like 0.4.
No, yeah, depending on the width of the function. So in this particular paper, it was some parameters were defined, but after that we did another work where this parameter was also learned. So I am referring to the first paper. This is the simplest one. So that can be varied. So later on, what we did was we used parameter tuning using the variables. Then you can vary the width depending on the data. Yeah. So in this case, so this was the pattern. So it was found to be closest to very medium. This was found to be closest to high. Other hybridizations. So this was what we did in neuro-fuzzy generation. Later on, we incorporated graph sets into this framework. I think Professor Pal introduced about graph sets. So this was knowledge encoding and classification, and we applied it to microarray gene expression also. So this is Neuro-fuzzy MLP, which was a pioneering integration for knowledge encoding using discernibility function, redux and dependency rules. So this Mohua Banerjee is in IIT Kanpur. So she was at that time there, and we did this work at that time. So hybridization of graph sets with neurocomputing for mining the initial topology of the knowledge base parameter. Now, you know that in knowledge base, in normal neural networks, in normal neural networks, what happens is the prediction weights are initially random values. So what you are supposed to do is you have to learn the prediction weight values during the learning phase. Now, what is learning? Learning is you are optimizing an error function. So what is there? The multiple weights are there in the neural network. So what is happening is the error function is in the very highly complex weight space. So it is a plateau and valley and peaks, lot of that. So in gradient descent, you have to come to the minimum. So you can come to local minimum, but your objective is to reach a good minimum. Now, when you are starting from a random location, you don't know where you are. You can convert, you may not convert. So what is knowledge-based network is, if you can start with some knowledge about the weight space, you can start from a good point in the weight space, then your convergence will be faster, because you are already at a point which is nearer to the minimum. You can expect that your convergence will be faster. So for that purpose, we use graph sets to extract some crude domain knowledge from the data, and we encoded that into the neural network architecture as a starting point. So thereby, this hybridization with graph sets allowed faster convergence and better visualization. So going back to the previous module, here we are building on it. We are introducing graph sets to get the initial topology. Topology means the architecture as well as the connection with them. Architecture means the number of nodes in the hidden layer. So here the hybridization with fuzzy sets was also there.
What about the number?
One.
That is always.
Yeah, we always had. No, here it was possible to get two, because you see, graph sets can extract rules in the form of conjunctions and disjunctions. So if you have an and or in a rule, then we had two levels. But in the example that I am providing here, going to provide here, it is only one layer, because we didn't have both levels. What we extracted ultimately was only and or, only or. So we modeled it as the and or was modeled as the hidden layer.
So your output is in terms of conjunction?
No, that is the output of the rules using graph sets on the crude domain knowledge to extract some crude rules which are mapped to a neutral network, and then that is trained using normal neural network learning, and you are allowing to grow with more connections. So the topology, initial topology starting point is fixed, the number of nodes. Only we are allowing the connection with values to be this two.
And your number of hidden layers and using some sort of hybridization. Know the number of hidden.
No, this graph set is determining the number, the rules, and that rule is giving the number of hidden nodes and layers.
But the hidden layer is using one.
In this case, it was one. It can be more. Yeah.
In any case, you don't need
You don't need more than two. If you, the more number of hidden layers you have, the more complicated and slow it becomes.
there is no.
No, not improvement, because you see, you introduce so many parameters to learn. See, so many the number of connection weights increases means the number of degrees of freedom increases. So if you don't have sufficient data.
Two hidden layers are sufficient for any.
Mathematically, Kolmogorov suggested one hidden layer is sufficient.
I think combined white put that more than two is more than enough for any application to any application.
Theoretically, one should be sufficient, but because you cannot have everything theoretically computed here, there is randomness involved. So you cannot go back to
And it was experimentally identified that more than two you will increase the cost, but there is no
cost is increased. So now again here we had, as before, the hybridization with fuzzy sets as the input and the overlapping membership at the output, and graph sets were used to extract the rules. Now graph sets have a very good mathematical property that they are able to extract something called reducts. What are reducts? If you have a number of features, you are able to extract the minimal number of features, which is mathematically established. So if you have small number of feature sets, naturally you are generating smaller subnetworks. So again, the cost of computation is less. So first what we did was we created a knowledge base classifying the objects and attributes within the decision tables, then removing some undesirable attributes, that means those which are redundant. This is called knowledge discovery. From the large knowledge database, you are extracting the useful features. and analyze the data dependency in the reduced database to find the minimal subset of attributes, which is called redux. So this is the algorithm. Let's say we have an n-dimensional pattern. This is represented as a 3n-dimensional fuzzy linguistic pattern, as I described earlier in the earlier form. So here what happens is, the low component, medium component, and the high component of the first feature, and so on for the nth feature. So from n we are getting 3n dimensions. Now this was in this work in 1998. Now after this we again did one where we had the actual values between 0 and 1. But in this particular initial, this pioneering work, the first work, we then set a threshold. If it is higher or lower than 0.5, we set it to 1 or 0. We clamped it to 1. So ultimately we got binary free and dimensional patterns. Not free in the sense, it is three-dimensional, but it could have multiple 1 components, multiple 0 components. If the value is greater than 0.5, we are taking it to 1. After this, we did another paper where we removed this constraint. So this is the first one. I am focusing on this one. It's simple. Now because you are mapping it to the binary pattern, you can get multiple same template for different patterns. Say somewhere you got 0.6, somewhere you got 0.7, both are getting to 1. So you could have the same template. So we compute the frequency of occurrence of the binary patterns. Select those patterns having frequency above a threshold for noise removal. Let's say you have 20 templates formed. So the first template has 10 patterns mapped into it. Second template has 5 patterns mapped into it. And there can be some templates which have only one pattern. So those are considered as noise, and we are setting a threshold on this frequency of occurrence of the template to keep the higher occurrence templates in the study. Here. Then we generate a decision table consisting of these binary templates. And we extract dependency rules corresponding to the informative regions or blocks. Let's say of this form. I have an example after this. So let us say a 2-dimensional case. Now this is the box which is completely enclosed in the set. In rough set you may have heard about lower approximation. So this is the lower approximation, and this corresponds to M1 and M2. So this is the physical meaning of how the rules are getting extracted. So this way it is providing a crude description of the class. So if this is the class, this is crudely represented by M1 and M2. And for the further detailed description, we will go to the neural learning. So this is rough set is used to set each of these crude descriptions into the neural topology. So we are starting from a better point in the search space. So for this example, we had the vowel data. So this is class 6 of that data. We had one, in those days we had a Telugu vowel data in our department, and everyone used to work on that. We also worked on that, and this is the 6th class of that data, and the threshold was 0.5, and these were the templates generated in the 3 dimension. It had 3 format frequencies, F1, F2, F3, mapped to 9 dimensions, and these are the templates generated. See, in this case you had 2 1s, in this case you had 1 1 only for the first feature. So it depended on the type. Now here we see that there were in all 41 patterns, and of these the first 20 patterns were mapped to the template, first template. The next 9 patterns were mapped to the second template. The next 7 patterns were mapped to the third template, and the next 4 patterns were mapped to the fourth template, and the rest, with this threshold, the rest were eliminated as noise. So now we consider that we have these 4 objects, y1, y2, y3, y4, and the attributes are L1, M1, H1, L2, M2, H2, L3, M3, H3. Now this work was actually done with my research scholar, that is Haidar Banka, who is now in Indian School of Mines. Okay. So then what happened was, we were computing, this is called the attribute value table. Discernibility matrix is computed like discernibility matrix. We say that we put in a value in that corresponding component when the attribute value for xi and attribute value for xj are not identical. So what is the meaning of this? Now you see, if you recall, there are 4 objects, y1, y2, y3, y4. So this is the matrix y1, y2, y3, y4, y1, y2, y3, y4. So this is the diagonal and the lower triangular matrix. This is same, so we don't need it anymore. So the meaning is, which are the attributes in which y1 and y2 are different? This means which are the attributes on which y1 and y3 are different. Different means you can distinguish between them or discern between them. Discern means distinguish. So from that we get the name discernibility matrix. So if you go back to this, if you look at this, you will see that y1 and y2 are different on m1 only. Others are all similar. So that's why here what we are putting is m1. Similarly, if you compare y1 and y3, you will find, if you compare y1 and y3, these are same. So m1 is different, then L3 is different, and H3 is different. So that's why we have m1, L3, H3, and so on. Like that we are doing for each pair. So for the entire class, the discernibility function is any discerning feature for y1, y2, and any discerning feature for y1, y3, and any discerning feature for y1, y4, and any discerning feature for y2, y3, and for y2, y4, and y3, y4. So in this manner you have to form it. So here what we are getting is m1, then and. So why or here? Because it is different either in m1 or in L3 or in H3. Any of them is sufficient to distinguish. That's why you have the or here. Now to get the whole function, you need the and in between. So it is this is a conjunctive normal form, right? So now you have to, so this is for the entire class. Now you simplify using common logic operations and you get this. Now we have to convert it to disjunctive normal form, which is the most complicated part of computation. Converting from CNF to DNF is very hard. So there are a lot of approximations for that, approximate solutions. Because in the real large space it is very complicated. But in this situation, we did it fully exhaustively because it was only 3 dimensions. But in the real case, you need to go for some approximation. So the disjunctive normal form was this. So once you get the disjunctive normal form, so you see these are the conjuncts which are separated by the or. That means either this is sufficient, or this is sufficient, or this is sufficient, or this is sufficient. So that's why each of these are called reducts. And this is mathematically established that of these 9 features that you had initially, any of these sets is sufficient to represent the entire information accurately. So that is what is reduct. Now you can choose any of these reducts for your further operation. So considering only the first reduct, let us say, that is M1 and L3 and M3, we again construct the reduced attribute value table. So this is the same table as we had before, only the attribute values are less and we have the smaller table. With that, we again construct the reduced discernibility matrix and get the rules. So for each, say for function, the first y1, for y1 means y1 and y2, and y3 and y1, and y4 and y1. So these are the three components, reduce it to this. For the second object, this is the rule. The third object, this is the rule. Fourth object, this is the rule after simplification. Now, the entire dependency rule generated for the whole class, in this case would be combining these. So here we have M1 or M1 and M3 or M3 and M3. Like this. So this is the whole thing, and this is again reduced to this. Now if you go back to the redux, for this operation we chose this reduct. Now you could have chosen this reduct also, you could have chosen this reduct also, and you could have chosen this reduct also. It may have given the same set of rules or may not have given the same set of rules. For this case, for this class 6, we had the other rules with the other set of redux to be this form. So there were three types of rules for the class 6. The physical meaning of this is that in a class, in a pattern class, there can be multimodal distributions. So each distribution can be represented by each of these rules. A particular class need not be uniform. So here we generated three sets of rules for class 6. Now, there were actually 6 vowel classes in that vowel data. So there were 5 other classes. So for these 5 other classes, following the same procedure of redux, we generated one set of rules, 2 sets of rules for class 2, one set for 3, one set for 4, and 2 sets for 5. And the dependency factor for each rule was 1 in this case. And so the total possible set of rules are then what? 2 into 2 into 3. That is 12. 12 possible combinations are there. So there are 12 sets of dependency rules, and each set of dependency rule was used to generate a set of networks. So we had 12 sets of subnetworks for the 6 classes. So what was the role of rough set here? The network topology was automatically determined from the dependency rules generated from the decision table by computing the relative redux and their dependency factors, and these were encoded as the initial connection nodes. The feature space or output classes provided the condition or decision attributes of the decision table. The hidden nodes modeled the conjuncts in the antecedent parts of a rule, while the output nodes model the disjuncts. Now we go to the example 12. This is one set of rules, and we are showing how the network is mapped. So you see C1 was, this was the rule, H1 and L2 and L3. So this is H1, here is the connection, L2, here is the connection, and L3, here is the connection. So this is the initial connection and topology for the network, and this is the class 1. And the dependency factor was 1, and here since we had 3 inputs, it was divided by 3, 1/3, 1/3, 1/3. So this was the initial value. For class 2 it was M1 or L3, so M1 and L3. These two came, and this is 1, and here it is half and half. So likewise, this was the initial network mapping using rough set after doing the extraction of rules. Now it was trained after this. And after training, final extraction rules were extracted, refined rules were extracted. Now this was when we introduced rough sets in the hybridization. After this, after introducing rough sets, we did normal backpropagation learning. So in this particular model, which we developed after that, this was in 2003. This was Mitra, a student who is now in IIT Kharagpur. So here what we did was, split a learning task into several subtasks, train a subnetwork for each subtask, and integrate the subnetworks to generate the final solution. So the strategy was divide and conquer, and the application was for mining large data sets. So here what we had was, this final training was done using genetic algorithms. So the hybridization involved all rough, neuro-fuzzy and genetic, all the 4 components. The merits were it provided effective scaling of the algorithm, speeded up the convergence, improved generalization, generated compact set of meaningful and less redundant rules or refined rules, and final network has more structured components. That means it is the redundancy is less because we are starting from a better point in the subspace. So ultimately when we extract the refined rules, they were more meaningful. So the classification problem was like this. We split an L class problem into L 2 class problems. So suppose there are 6 classes. So the 2 class problems would be class 1 or not class 1, class 2 or not class 2. So each is taken care of by a subnetwork, and that subnetwork, the 6 sets of subnetworks are finally merged by genetic algorithm. They are concatenated. The intramodular links are already evolved within the subnetwork and they are kept unchanged, while the between subnetwork or intermodular links are now initialized to low values. And the final network is trained such that the intermodular links are adapted more with higher mutation as compared to the intramodular links. So that means, so the domain knowledge was incorporated by rough sets. GA was used to tune the whole thing. The output was the membership value, input was the linguistic value. So this is the schematic diagram to make you understand physically what is happening without going into mathematics. So let us say these are the subnetworks. Each subnetwork has been encoded using rough sets. So let us say in the feature space you have got such crude approximations. Now each subnetwork is trained by ordinary GA. So these are the partially defined subnetworks. So each region is getting partially defined and getting better equipped to handle the decision bound. And eventually all these subnetworks after partial training, they are concatenated together. So when they are concatenated, the between subnetwork links are having higher mutation probability, that is these dotted values, and already existing within subnetwork links, they are having solid values or they are having low mutation probability. That means what has already been learned is not going to be changed further. It is going to be changed less, and what is remaining is the between subnetwork links. And after that training, you will get the better decision boundaries in the feature space. Genetic algorithm. Because we are not choosing the algorithm by the way. We are just training the network. Variable mutation is for these links. See, these are the subnetworks. So these connection weights are already set up. They are good. We don't want to disturb them. So these will be trained. Now when they are concatenated together, they will get joined. So these will have low mutation probability. So they are not changed more. But when you connect this to this or this to this or this to this, that part can be changed now. So that is having higher mutation probability. So we are sort of freezing what we are already learning. Yeah, it's in chromosome. This is chromosome. I don't know if I have the slide. Let me see. No, it's not there. It's in the chromosome. The connection weights are in the chromosome. No, the physical implementation is in the form of tree. The chromosome is a string. You have to keep track which is linked with what. So there when you are doing, you have to mark the bits which are going to have low mutation, which are going to have high mutation. Because we don't want to change what we have already learned in the subnetwork. So that is going to have low mutation probability. And those which will be learned now will have high mutation probability. So on the vowel data, you see this is the first normal MLP. This is the fuzzy MLP. Yeah. So as minimum as possible. So among that, even lower value is given to those and comparatively higher value is given to median. So if your low value is 0.001, let's say, we make it 0.000001 for the within class, within network. And for the, that is low and high is relative. Within that low value, you can have lower and high. It doesn't mean you need to find out. So here you see, this is the normal MLP, this is the fuzzy MLP, that is a 1995 work. This is the rough fuzzy MLP, 1998 work. And this is the modular version, which is this 2003 work. So gradually the performance, classification, accuracy is going up. And here we find that the network size is coming down. And here is the training time, that is also coming down. So this was a family of networks actually we developed. So this was that vowel data we had. And these were some sample rules ultimately extracted. This was how the certainty factor was computed. And we see that this is the class O. In vowel, this is the Telugu vowel. You have the 6 simple vowels O, A, O. All languages have that, all Indian languages. So this is O. You see very much overlap. This is R. This is E. It has the E and the E. 2 E's we have. U also we have 2 U's. So these are the U's. This is the A. O we have in Bangla. And in Bangla we have O. All Indian languages have these. Most Indian languages. So then here you see this is the sample rule for class O. It was M1 or M2. And the third dimension is not shown here. It is the 2-dimensional figure. So you see it is matching M1 or M2, medium of this and medium of that. It is matching. And the certainty factor was computed as this. So this is after all that Doom generation. This is not classification. So Doom generation with graph sets, you are having the network and then you are using the genetic training. So after the connection weights are analyzed, then we are extracting the weights. Then finally the application to feature selection as applied to microarrays next section. If you are aware of microarray gene expression? So this is in bioinformatics, this application. We won't go into detail. The thing is, in gene expression data, the genes are the features. You've got numerous number of genes. Let's say it's a very peculiar data where if you have 30 or 40 samples, you can have 5,000 features. So of all these features, only very few are important. So that means for a particular disease condition, the genes have the information. Now, because every person's gene values are different, they express themselves in a different manner. That's why all of us are different. We look different, behave differently, and even the same person, when you have a disease, you have different values. So a cancerous region, cancerous tissue and a normal tissue, you have different values of certain genes. But it is found that for each condition, only a few of these genes are important. So in this scenario, feature selection becomes very important because a large number of features or genes are not relevant to the description of the problem. And if you have too many useless genes or useless features, redundant features, it can degrade the decision-making performance by masking the contribution of the relevant features. So we need feature selection. Now, why rough sets and multi-objective GA? Well, you were introduced to genetic algorithm yesterday. Did you understand about multi-objective genetic algorithm also? So yeah, multi-objective means it should be conflicting conditions, right? So here we need that. Why? Because why rough sets? Because redux in rough set theory correspond to the minimal feature sets necessary and sufficient to represent a correct classification decision. It is mathematically established. So redux can classify among all elements of the universe with the same accuracy as the starting attribute set, and also are of smaller cardinality. If they are smaller cardinality, then the computational complexity is lower. And the conflicting nature of these characteristics requires the application of multi-objective algorithms. Why conflicting? Because if you have less information, your performance is likely to go down. But again, we want less information, but we want high performance. So these are conflicting conditions. That's why we need to apply multi-objective optimization. So this was this paper. Was Momo Banerjee, myself, and Haidar Banka. So that was in 2007. So solutions were represented as binary strings of length n, where n is the number of condition attributes. It can take on value 1 or 0. 1 indicates the presence of the corresponding attribute, and 0 indicates the absence of the attribute. So it has got shifted. LV is the number of ones in the redux candidate, and this LV. And V is the number of objects discerned between, and CV is the number of objects in the two classes N1 and N2. Now the two objective functions are defined like this. So these are the number of ones. So N is the total number of attributes, and LV is the number of attributes we select by our algorithm. So if this value is lower, then this value will be higher. So a higher value of F1 means there are lower number of features we have selected. Similarly, F2 is, CV is the number of pairs of objects which can be distinguished. We want this to be higher. We want this LV to be lower. We want CV to be higher. CV is higher means F2 is also higher. So it determines the discernibility between objects. Now, we could also have used single objective GA, where in a one fitness function we could have put in alpha 1 F1, alpha 2 F2. But the problem here is that you would have to select the parameters alpha 1 and alpha 2. Again, user defined parameters. So if you use multi-objective GA, you get rid of these parameters. So this is a small example to explain what is happening. So in this case, let's say there are 8 attributes. So a string is of length 8, and 1 means that feature is present, 0 means that feature is absent. Now for this particular string, here we assume there are 2 objects N1 and N2 in one class, and there are 3 objects N1, N2 and N3 in each in the second class. So how many pairs of objects we have from both the classes? M1, N1, M1, N2, M1, N3, and M2, N1, M2, N2, M2, N2 between each pair of classes. This is a 2-class problem, just to explain the situation. Now for this particular string, if we look at the distinction table, we find that LV is 3, that means number of attributes present is 3. And how many pairs of objects it is able to distinguish between? With the first attribute, if you look at this column, you will find that it is able to distinguish between this pair and this pair and this pair and this pair. pairs. So 4 pairs of objects can be distinguished by the first attribute. Taking the fifth attribute, what additional information we get is again this pair is able to be distinguished. So the total number of objects now is 5. These are all same information, no additional information. And with the last bit, we gain no further information. So CV, the number of pairs of objects being discerned is 5. And the total length of the string is 8. So according to the formula, F1 becomes 0.625 and F2 becomes 0.833. So like this, different strings are applied to the algorithm and the multi-objective GA is run to get the optimum set of features. So this is the sample result on these are 3 publicly available microarray gene expression data sets from the internet. So colon cancer, lymphoma and leukemia, 3 kinds of cancer. And if you look at it, you see the number of attributes or number of genes. See here 2000 and number of samples is 40 from cancer and normal tissue 22. Again here it was 4026 and these are the samples, 2 types of lymphoma. And 2 types of leukemia, ALL and AML, 47 and 25 and these are the number of genes. We did some pre-processing to reduce the number of genes and these are the results after using our algorithm and multi-objective GA. So from 2000 we could reduce it to 9 with no reduction in performance, classification performance. Whereas using single objective GA, these were the number of genes reduced. So this was the advantage. So for colon data, the performance, classification performance using K nearest neighbor classifier with the reduced set of attributes. Again for lymphoma data, and this is for leukemia data. The performance is higher and the number of features or genes is also less. This is the how the feature selection varies. As with number of generations with GA, the number of attributes goes on increasing with different population sizes. This is from that paper actually. And this is the Pareto optimal fund we generate for the multi-objective GA for colon, for leukemia and for lymphoma. And so with that, so thank you so much.
Second person, the attributes are there. Like that, there are 40 cancerous tissues from people having colon cancer, and 22 normal people, their tissues from the colon region without cancer.
So that translates to 2000 genes.
2000 genes in that tissue
Okay.
of all the persons.
Oh.
40 from cancerous people having colon cancer from that colon cancer tumor tissue, and 22 normal people from their colon tissue, but that is normal tissue.
So in total, we have 62 samples. All 62 samples will have 4,000 attributes. All 62 will have 3.
That is the expression value of the genes. That is publicly available in the internet. Now, what people have to do these days when there is collaboration, what happens? You need a wet lab. Then the wet lab, the biologist will extract the gene expression values from the volunteers or from the patients, the doctors can extract. But that is also a difficult part. You need collaboration, you need money for the equipment. So what people normally used to do is, this was also done some years back. So the easiest way was to get from there. And the other advantage is, because you are taking the publicly available data, many people have worked on that. So you can compare your results. But if you take some new results, you don't have the benchmark. It's a very difficult situation.
So ma'am, with this result, you are saying only 2 genes are able to classify whether it is having a patient cancer or not. So don't you think it is losing the information?
No, but the thing is, in this
whether these two any newcomer, right?
You can.
Now the doctor, the biologist has to verify and find out
Whether
how
it-
good these two genes are.
Whether someone has verified it or yet not.
At that time, what we did mathematically, that was done. After that, we did some work where, there are ontologies present in the
If some system biology, some network, whether this network is present in the system, actual system or
This
not.
is not network. There is some gene ontology study and all that. So nowadays, what is available is you have some p-values. P-values provide the biological validity of the particular gene with relevance to a particular disease. There are some statistical evaluations done there. So again, you have to match with that and see whether how good is the p-value for your cluster. Suppose you obtain a cluster of genes. All genes are not equal.
That is true, but only two genes.
But mathematically, it was seen that it was
Mathematically
Yeah.
or biologically.
So this one was done nothing.
Mathematically.
This was 2007.
Okay, that's the first
But
question.
biological view of it is also
Yeah,
important
biological
because
view.
finally we want to produce a drug act. Finally we want to produce a drug so that we can cure the patient.
Yeah,
Biologically is
so
also
there are
important.
now databases where they provide or study the literature and find out that there are some genes which are known to be cancer causing. Now then if you can match yours with that, then it is established that you have found a gene by yourself.
But ma'am, what pre-processing you have done here?
There we did was some sort of like if there were very similar values for over the samples. It was not varying over the. I'll give you an example. Let us say there is a particular gene X, which is not varying much over cancerous tissue as well as non-cancerous tissue. Then you can easily see that it is not influencing the situation in any manner. So that can be eliminated altogether. We were checking the expression value, checking how much it was varying over all the samples. If it is not showing a marked transition between the two classes, then it is not relevant for that disease. Now you see, of the 2000 genes that are present there, maybe for the colon cancer, only a few are important. Maybe for some other situation, the other genes are important. And not what this shows is not that the 2000 genes are useless, not that. For this particular situation, 2000 are not necessary.
In colon cancer, some are not necessary. So you need that.
Yeah, if they are not varying over the normal and the disease tissue, it's obvious that it has got no value. It is redundant. If it is fixed, let's say it's always near 0 or always near 1 or always near 50, let us say. It's not very. You see, for a particular person also, even when you are healthy, still over age, the gene lines get skewed. So, for example, when a person is young, the features are different. Then maybe the hair will gray, or the hair will become sparser. So that is due to the value of the certain genes which are changing. And when you go to a very cold region, you go to Antarctica, all your attributes will be changing. Your expression values will also be changing. So like that, they are. Of course, the time information is also
It's also important.
Yes.
Time.
What are the information we can get from gene ontology?
In ontology, you can get like these genes are cohesive in nature, these genes match with each other, and this group of genes is very meaningful in such a disease condition or such.
Ma'am, in case of membership functions, we have two functions, Mamdani and Sugano. So is there any, when we should use?
Not in this one.
No, not this one. In previous, in fuzzy inference normally, just we have Mamdani and Sugano. Is there any standard rule when to use which?
Please repeat your question.
In fuzzy inference systems, we have, for membership functions, we have Mamdani function and Sugano. To construct rules. So is there, when we should use which one?
Yeah, what
is
is
there
your
any?
objective? You have to find out what you want. If you want very high precision control or something like that, then the high precision supernode will be important, but the complexity will be higher if you are computing. But if your objective is very simple and understandable, you will go for the Mamdani. So it depends on the
There is
objective.
no-
Rule is there, na? One crisp, then Mamdani, otherwise rules.
Yes.
Then our
I was just asking, is there any specific other standard?
Then if you are, then
हाँ,
otherwise
one is-
then
I saw Takagi. He is not a very old person. Sugan was student. He is now doing no more fuzzy, doing something else.
Ma'am, what time, in what system did you simulated this for? What configuration? In very high processing or
Not very
or
high. In
normal?
2007 it was published. That means it was done in 2006. Compared
What-
to today,
how
it
much
was.
time will it
But
take?
no, it took some time.
30 minutes, 1 hour, 2 hours,
I don't remember now. Either will know.
1 day,
Not whole day.
not whole day.
2007 machines were much powerful. Yeah.
No, this
Nowadays
takes much time,
configuration
very
is-
much time.
No, we did the pre-processing. We got it reduced. We got it reduced after the pre-processing.
And still it is 3,000.
Yeah, it is 3,000, but the number of samples is not very big.
Sample is not a big deal in
But
cancer.
what type of
data.
operation are we doing? What type of operation? It is two-class problem. So once you have
That what I want to ask whether it takes 30 minutes, 1 hour, whole day.
I don't remember. You better give an email to Hyder Banka. Look at the paper and send me.
Because my
So
program.
there is Hyder student. You can ask.
I will give my mail ID to you basically.
Okay. Any other questions?
If not, then we will thank the speaker for giving such a beautiful talk. After this, we will move to the tea and then followed by the Wednesday session.